Blue long in mode.
Just so you all know, I have started recording the meeting. So the entire class will be recorded. Okay, so it is now 9:15, and thus time to start this lecture. My name is Ignacio Gonzalez, and I need you to tell me that you hear me and that you see my screen, preferably in the chat. Oh. The lecture will be available on Canvas, but it's not yet available. So it will be uploaded once we're done. All right, I'll keep an eye on the chat, but not live. So don't go crazy with the questions, and every now and then I'll have a I'll have a look. Is it possible to upload the lecture immediately? Well, not for me. Sorry, this is my first lecture using Zoom, and I have no idea how to do it. So it will have to wait. Okay, today we're going to go through the numerical evaluation of a dynamic response. If you have followed the course plan so far, you have already gone through how we can calculate the maximum dynamic response using things like the dynamic amplification factor. If we have a sinusoidal load in our structure. So, but in this lecture, I'm going to explain how to calculate the dynamic response of any structure or for any load. That it doesn't need to be sinusoidal, it could be any type of load. Okay, and I'm going to give you through two different methods for the calculation of the dynamic response of a structure. One called the central difference method, and another called Newmark's method. As you can see in the Newmark is methods in plural, and that is because Newmark is really a family of methods and not only one method. But we're going to go through all of that. Then I'll mention something quickly about Duhamel's integral, the second point in the slide. And finally, a kind of reinforcement on what you have previously learned about modal shapes and what they mean. All right. Here you can see where the different sections are in the book. If you want to read it for yourself. We're not going to go through all the chapter 5, which is the one that primarily deals with the simulation of structures, of the dynamic of structures. But we're going to go through at least the beginning of it, which is the part that talks about linear methods. In this course, we will limit ourselves to linear structures. and thus we will not talk anything about the nonlinear, which is the second half of this chapter number 5. All right. Something that you should by now recognize is what it's called the general equation of motion. All right. It's the one being shown here. We have a structure that has a mass given by m. It has a damping given by the damping constant c, and it has a stiffness, which is given by the stiffness k. This, of course, this is an equation that equates forces. So we have forces on this side, but we also have forces on the other side. And as we know, we have that the force is proportional to the mass times the acceleration, all right? These two dots indicate the second derivative of u, which is the displacement. So the mass times the acceleration is a force. There's another force involved, which is the damping times the velocity, because the force of damping is proportional to the velocity at which this particular structure is moving. And then we have the stiffness, of course, times the displacement, and has this work like any idealized spring, which produces a restoring force proportional to the displacement. And these are known like as the forces internal to the structure. And this has to be equal to the forces external to the structure, which are symbolized here by P, which are the load that are affecting the structure. And as you can see, P, it's a variable. It changes with time. So P can take any form during time. So if we were to draw it, the force P with time, it could take absolutely any shape, weight, or form that we want. And with this formula, we should be able to calculate it. So we are not limited to only sinusoidal shape forces. And of course, as you can see, this is a second order differential equation. We have the first derivative and the second derivative of a quantity of our unknown u, which is the one that we want to solve for. And thus, we need two initial conditions, right? In order to be able to solve a second differential equation, we always need two extra conditions. And in the case of a structure, it's, I would say, 99% of the time, the displacement at time 0. So normally the structures are not moving at time 0. If we have if we are trying to calculate, for example, the vibrations of a bridge when a train crosses it, then normally we would assign the value of 0 to the displacements of the bridge when there is no load. Thus, before we started simulating, we have an initial value of 0. And we also have normally an initial speed. Okay, so the value of the speed at time 0, and this is also normally 0 for structures. It doesn't need to be 0 if we're considering other, for example, if we're looking at the machine or a vehicle or something like that. This equation also applies to them. But in the case of a structure, normally the structure hasn't moved yet before we start applying the load, and it's static, so at 0 speed. All right. Now, one problem with this equation is that, as you can see, it is an equation that needs to be fulfilled at every single point in time. So the sum of these three quantities needs to be equal to this quantity at every point in time. And that, of course, means an infinitely amount of points. So if we want to simulate, for example, the response to an earthquake, and the earthquake is 1 minute long, well, then we would need to calculate the response of our structure to this earthquake, ideally in an infinite amount of points, everything from time 0 to time 10 minutes or whatever we want. And that is, of course, impossible from a computational perspective. The computer cannot deal with that. So what we do is we discretize time. Okay? That means that we choose specific intervals of time for which this equation will be satisfied. So if I were to try to draw this, let's say that we have the displacement u that we want to calculate and time. And we could imagine that the real response of the structure would be something like this. I'm just making it up now. This is the real response. But of course, this involves infinite points all through this curve. But in order to make this process more computer friendly, we're going to calculate the response at given intervals. So at this point, at this point, at this point, yellow was not a very good color to choose. So go with green instead. At this point, okay, so that my computer program will be able to know what the displacement was there, and there, and there, and so on. So the green is the we can say calculated response. Theoretically, we will have no idea what's happening in between. So all this, the values here between 2 points are going to be unknown to us or to the computer. But the technique or the way we do this is that we choose the delta t small enough so that we have a representative idea of what the structure is doing. So this interval of time between the points between different points that I choose to calculate, this is called the delta t. Okay, and the point is to choose it small enough that nothing very interesting can happen here, right? So for example, if we're going to calculate the behavior of a structure, how it responds to an earthquake, then maybe we choose a delta t that is equal to 1/100th of a second, okay? So we will know what the structure is doing at 0.01 second, and we will know what the structure is doing at 0.02 seconds. And ideally, the structure cannot go very far in 1/100th of a second. So by choosing a delta t small enough, our result, which will only be valid at certain points, will be good enough from an engineering perspective, because we don't want the mathematical solution to this equation to be perfectly exact. We just want an approximation that is good enough for our engineering purposes. Okay. All right, and so this is pretty much the same idea. We have here the equation that it's continuous in time, and here we have discretized the equation. So we're not solving for here, we're only solving for some values of p, for where we, like a finite number of them that we have to choose, while here we were solving for all the values of p. Because of course, if the let's try to go again, in the same way that we had to discretize, that we were going to calculate a discretized response u to the this value of u, which is our solution, which is what we're looking for. We also have to discretize the value of p, because p is a curve, of course, that varies with time, but we are not going to solve for every time. We have chosen to solve at discrete intervals. So thus, we also need the value of p only at these discrete intervals. Right? So in this equation, the u has been discretized, the p has been discretized, and because u is discrete, it's only a number of points, then obviously automatically the speed is also discrete and the acceleration is also discrete. It's no longer a continuous value with infinite variables through time. It is, let's say, a list of points. So I would have a value for p, a value for u, a value for u, the first derivative and the second derivative, and for each time, for my initial time, and then for the next time that I choose, and the next, and the next, and so on, until however many I want to calculate. And then I'll be, of course, all these values are given, right? The force is an input to our calculation, so we need to know it before we calculate. But all these other values I'm going to calculate. Okay, all the values for the displacement and for the velocities and the accelerations. And because this is now a list of values and not an infinite set of them, this is a much more computer-friendly problem. Okay, so we have gone from this, which is true for all times in an interval from the initial time to the final time, to this other version, which is only true in a finite number of points that we set. Now, this would, if I draw again, for example, the response u in time, And now we zoom in, right? So this is like a very zoomed in version of what we were drawing before. Now I have the value here and maybe the value here, but I know nothing what happened in between. So here, something crazy would happen, but again, by choosing this distance to be small enough, we make sure that nothing very crazy happens. But this distance is to be chosen carefully, but we're going to talk through, about that later on. Okay. For our applications, normally we keep the delta t constant. Good. Sorry. Cooperating. The delta t is constant, so that the distance from one point to the next is always the same. This doesn't need to be the case. Okay, we could write a program that calculates the displacement or the forces or whatever for at this given intervals, but then later we just switch to another interval so that we calculate them, I don't know, much closer together or much farther apart. That would depend. It's completely up to us. We have absolute control over how we choose these times that we want to calculate. Now, for the sake of simplicity, we're going to keep a constant delta t, but there are cases for which it's interesting to vary the delta t. Okay, for example, if we have an explosion. So normally, if we have in the normal case of a structure that is subjected to an earthquake or a structure that is subjected to moving loads, having a fixed delta t is enough. But if we're talking about an explosion, then it's not the case anymore, because explosions are very, very sudden. Of course, everything happens in a space of under milliseconds. So for the exact moment of the explosion, maybe if we had an explosion right here at this point, then everything after the explosion we would want to calculate with an extremely small delta t. But then after this time has passed, then we can go back to our more our larger delta t, because of course it takes time for the computer to calculate each one of these points. It doesn't take much time, but it takes some time. So if we choose a delta t that is too small, well, our calculation will be more accurate, but it will take longer time. All right. There are several methods to calculate this response, to simulate the response. As I told you, we're going to go through only 2 of them, but all of them have this property, which is very important. And that means that as we make the delta t smaller and smaller, our calculation should be closer and closer to reality. Okay. Of course, how close we want to get to reality would depend on what we need for our engineering purposes. Is 1% error enough? I don't know, is 10% enough? Well, completely depends on what kind of calculation we want to do, and that is up to the engineer to decide. But we want the method that in theory could have infinite accuracy. Okay, then in practice it will never be, but we don't want any method that is limited by to an accuracy. Okay, and all these kind of methods can be categorized into explicit methods and implicit methods. And the difference is a little bit subtle, but it's important. Let's say I'm going to draw the same graph that I've drawn 50 times today already, but we have the response with time. And we have the real curve that can look anyway. That is the exact solution. And we have calculated the response at some interval. Okay, but let's say that we are currently here. We have calculated up to here. Let's call it Ti, and we want to calculate the next value for in this case, the displacement. And we don't know where it's going to land. Is it going to be here or here or here or here or here? Like, we don't know. Okay. That was supposed to be a question mark. Maybe we can write that. So, an explicit method uses the fact that this is true. So this is the fact that the equation of motion is true at this point, at the latest point that we calculated. Okay, so with this fact that I'm going to label fact number 1, plus some assumptions that we're going to discuss a bit later on, it uses these two things to calculate, to project the response so that it can get a new value, all right? And that makes sense. We have calculated the response up to here, up to this point. Because we have calculated it, we know that it's going to fulfill this equation because that's the way we calculate it. And we do some assumptions on what is happening in this time interval. So the assumptions that we're making, they apply to the interval in between this point and this point, so that we land on the next point. So these two facts combined together will give us the next value, the value at Ti plus 1. Okay? But now the problem with these methods is that there is no guarantee that the equation of motion, this one, is going to be satisfied at T, at where we land. Okay? So I'm going to zoom in the graph. We have a displacement with time, and we had a curve, and we calculated this. This is already known, and we want to calculate the next value. The equation of motion will be true at the original point, because, and we're going to use some assumptions for the intervening time, and we're going to land at some point here. But the equation of motion here, it will most likely not be true, that the mass times the acceleration plus the displacement times the speed plus the stiffness times the displacement. It will not be true, okay? Hopefully, if our method is good, they will not be very far away from each other. So it will not be like a horrible, horrible difference. But anyhow, it remains the fact that this is not guaranteed. There is no guarantee that we are going to land at a point where this is true, where this equation is fulfilled. Okay? That was an explicit method, the one that I was talking about. So we using the equation of motion at the point that we had already calculated, plus some assumptions, we arrive at a new point. Now, the other type of method is the implicit method, okay? And these do the opposite. If I draw again, we have a displacement and the time, and we have a curve, and we have a point that it's known, and we have a point that we want to know. When we're using an implicit method, we also use some assumptions about what is going to happen here, but we put as a condition that whatever happens, whatever the method chooses to calculate, it will be true that the equation of motion is fulfilled. Down here. We want a method that guarantees that that this is true at the new point. Okay. Why do we have these two different methods? Why would we want a method that does not guarantee these? What are the advantages of an explicit method? Well, to put it shortly, an explicit method is much easier because we only use facts that we already know. We use all the values that we have already calculated to predict the new value. And we don't care what happens to that value. We hope that our method would be good enough to land on a decent value, on a value that is close enough. Okay? The implicit method, we are trying to guarantee things about the new value that we want to calculate. We have calculated the values of the displacement, for example, up to a certain point, and we want to calculate that the next value that comes has some properties in that it fulfills the equation of motion. So therefore, these methods are a little bit more complex, but they're also more accurate because we are trying to we're trying to give some properties to the new values, to values that we do not yet know. So then, yeah, they result in a little bit more complexity. The explicit methods, they are much simpler and much more intuitive, you could say, but they are less accurate. Okay. The first method that we're going to go through, called the central difference method. It is an explicit method, okay? To repeat, that means that we're gonna use only the values that we already know, plus some assumptions in order to calculate a new value, and we don't impose any conditions on the new value that we're going to calculate, okay? This method uses two approximations, okay? Those are the assumptions. I told you that any method needs the assumptions. Well, these are the two assumptions that this method uses, okay? What do these assumptions mean? Why can't I clear the screen? That wasn't good. Oh, well, whatever. Now there are two lines there forever. Let's draw the same graph as always. With red. Okay. This is time sub I, and this is time sub I minus 1, okay? And these two are known, should be known, because we have already calculated, they are like in the past, and we want to calculate the new one, which is in Ti plus 1, okay? As you can see, we are saying here that the speed at this point, which means the slope, right? The speed of something is the slope of the curve. We are approximating this slope by the difference between that one and that one divided by 2t. So we are this expression here is this slope. Okay. So one condition that we're imposing is that we're saying that, okay, we think that this slope here, the distance between the vertical distance between these two divided by the horizontal distance between these two, it's a good approximation of the speed at this point, okay? Which is an assumption. It's not going to be always true, but it is a very good approximation, okay? So this is what what this equation means in practice, right? That we approximate the speed of our structure at a, meaning the slope at a certain point, by this other slope, which is not exactly true, but it's close enough to the truth, particularly when these 2 points are very close to each other. What this other structure is what this other equation here is doing is something very similar, but it is for the speed, right? So if I were to draw the exact but this time for the speed, not for u, but the derivative of u over time. We're saying the same thing. We're saying that the acceleration, which is the slope at this part, right? The slope of the speed is the acceleration, will be approximated by the slope, but by this other slope. Okay. This is less obvious to see because this equation is a little bit more complicated. But if you do the algebra, if we write that the acceleration is equal to the new speed minus the old speed divided by 2 delta t. So now these two equations are the same, but here with the speed instead. And then you're going, with a little bit of algebra, you can see that this equation and this equation are identical. Okay, but I'm not going to do it here. Anyhow, we have now an expression that it's a good approximation of the speed, and we have now an equation that it's a good approximation of the acceleration, right? So we can just substitute it. So this value will go here, where the speed was, and this value will go here, where the acceleration was. And once we substitute it, we get this equation, right? So we have still the same thing that we'd always had. The mass times all this thing, which was the acceleration, and the speed times, this is the speed, times the damping, and the stiffness times the displacement equals to the force. So this is the same equation that we've always had. We just replace these values with their approximations. And now, as you can see, this equation, this new mess that we have created, it has only one unknown, which is this one, which is repeated twice, but doesn't matter. Okay, all the other values are known. We know what m is, we know the delta t, we know the previous value of the displacement because we have calculated. We know c, we know the previous value, we know k, we know the previous value, and we know p. So we can solve this this equation, and once we solve it, we're gonna get, that will give us the, so if we start with u0. That this is an initial condition. It has to be given to us, and we would use it to calculate the u1, And when we have once we have a U1, we can use that to calculate the U2 and that to calculate the U3 and so on. So given that we have an initial condition, which is normally 0, like I told you before, then we can proceed to calculate all the different values of the displacement if we have all the properties of the structure, that is M, K, C, and the forces P. All right? So that is the central difference method in a nutshell. There are a few more details to talk about it when it comes to the initial condition, but I think I'm going to take that after the pause. So I'm going to pause the recording now, and we'll take a 15-minute break. If I found where to pause this. Yes, sir. All right. So it's now 10:15, and I thought we could continue with the lecture. We were talking about the first method for calculating the response of a structure to a dynamic load. To sum up, this method required a few things. First of all, of course, we need to know the properties of the structure. That means that the mass needs to be known, the stiffness needs to be known, the damping needs to be known. And of course, it requires of us that we know the forces that are acting on it. We cannot calculate the response if the forces are known. But these are facts that we can normally calculate, given the design of our structure. And the forces are normally given by the norm, right? If it's the case of an earthquake, we have the norm indicates what kind of accelerations we should put. If it's the case of a train bridge, then the norm tell us what the axle load of each train wagon should need. It requires also that we calculate or that we choose, sorry, a delta T, that it's up to us, up to the engineer. And it also requires that we have initial conditions, right? That we have the value, the original value of the displacement, which will in 99% of the cases be 0, and that we have the initial value of the speed. And that will normally also be 0. Okay, with all this information and this formula here, we should be able to repeatedly use the same formula in order to go from U0 to U1 and then U2 and then U3, etc. Okay. Again, this method is a method, belongs to the family of method that we choose to call explicit. And it's called explicit because we use the equation of motion, this equation, at the value of t equals t sub I, okay? If I go back a slide, And here we are using the equation of motion at t sub I. So we are assuming that the forces are in equilibrium at the point in time that we have already calculated. And we are using these two extra assumptions, 1 and 2, to calculate the next moment in time. But there is no assurance that, that this equation will also be fulfilled in the next moment in time. It will be approximately true, but not exactly true. Okay. If you have been paying attention, then you might have discovered a problem. And that is that the calculation requires us to have it requires to have two previous values. In order to calculate this value, we need the previous value, but also we need the one before that, right? So if we want to calculate U5, for example, well, in order to do that, we need to know U4 and U3, which is fine because we are calculating one at a time, so we have both values. But what do we do to calculate U1? So the first value that we calculate. Well, for that we would need U0 and U minus 1. And there is no U minus 1, of course. We're trying to calculate we're just starting our calculation. There's nothing happening before that. And for that, we use we use a fictitious value of U minus 1, meaning something we invent, okay? We are giving the value, these two values were given. These are the initial conditions. the initial displacement and the initial velocity. And because we have those, we can calculate the initial acceleration, okay? So these are given, this one is calculated. And we use the same formula that we had been using before. We use these two approximations. We use them again here and here. Here and here. Okay. And they would give us this fictitious value of U minus 1. Because again, as you can see, now we have two unknowns here. When we started from the initial conditions, so we have U0, and we want to calculate U1. Well, U1 is, for the time being, this is an unknown that we want to calculate. And we have another unknown, which is U minus 1, which doesn't exist yet. But we have two equations, okay? So these two equations together will give us the values of U1 and U minus 1. This one is useless. We don't need it for anything, but it's needed for the calculation. This is the one that we're interested in. And once we have U0 and U1, with these two together, so we can just apply the previous rule to calculate all the coming values, right? and so on to infinity. This is a way to implement this the algorithm that I have been describing with words so that you understand how it works, but with formulas, all right? So this is taken from the book, all these formulas. They are from an older version of the book. Of course, there are an infinite way of calculating. Like you can program it however you want. You don't need to do it in the, as long as it's the same formulas, how you program it doesn't really matter. What matters is that the formulas are correct. So the formulas that are here are from an older edition of the book. I think the newer edition have a slightly different way of programming, but the formulas do the same thing. So you can, when you have to program this method for one of the exercises, you can use the formulas that I'm giving you here, or the formulas that are that are in the later in the book, or you can just take your own understanding of the formulas in this lecture to do it in your own way. You don't have to do it this way. But this is one way of doing the calculations. So, of course, like I said before, the values K, M, C, and P need to be known for all times. The value of delta T needs to be chosen, and the values of UC and these initial conditions need to be also known. Okay, but once we have them, we can calculate the initial acceleration. With that, we calculate this fictitious u minus 1. And then we calculate these three values, okay? K, A, and B. They have some meaning in physical terms, but they're not very important. But what's important is that they're constant, okay? For a given structure, these three values, K, A, and B, are constant. They don't change. So we calculate them only once. And once we have calculated them, then we proceed to perform these two calculations, which we do time and time again. Okay, so this one and this one. So all this side are initial calculations, so they are performed only once. But these two calculations, they are performed like as many times as you need. Okay. So you calculate this p hat, and you use that plus this previous value of k that you calculated originally here to compute the new displacement. And with the new displacement, you calculate the new p hat, and you obtain a new displacement, and so on and so forth. Okay. So this is this is your loop in the calculations. If you do it in MATLAB or Python or whatever, this will be what you're looping. And of course, you have to store the results somewhere in some vector or matrix or whatever. So by the end of the day, you're gonna end up with a vector U, okay, in MATLAB or whatever, which has all the values that you have calculated. U0, U1, 2, etc. Okay. The other values you don't need to store. this p hat, it's something that it's just like an intermediate step for the calculations, and then you can override it. There's no need to say it. In this method, we can, if we want, we can calculate also the speeds at each time step using this formula, and the accelerations using these formulas. This is the speed and this is the acceleration. But of course, it's not required. It's not a part of the it's not an integral part of the method. But in the case of so if we're only interested in the displacement, then we only calculate the displacement. In some cases, you might be interested in the accelerations. For example, if you are designing a pedestrian bridge, there are limits on what the acceleration is allowed to be, because if it gets above a certain threshold, it becomes uncomfortable for the people walking on the bridge. So then you might want to store also the acceleration that you can check that you fulfill what the norm says should be the maximum acceleration. Okay, that was the explicit method called the central difference. And now we're going to talk about this numerics method, which is an implicit method. Again, the difference between implicit and explicit is that the implicit uses the equation of motion and makes sure that the equation of motion is satisfied at the point in time that you're trying to calculate, while that's implicit. The explicit just assume that the equation of motion is true at the point in time that you already know, and kind of hope for the best. Hope that wherever it lands, it will be close enough to the reality. Okay. Okay. So, if you remember from high school physics, we have the equation for uniformly accelerated movement. Okay, we have that the speed, let's say, at some point in time, it's equal to whatever the speed was before, plus the acceleration times t, right? That's the equation of a uniformly accelerated movement for the speed. And that is exactly the same thing we have here. Okay. So the numerics method, or family of methods, this implicit method that we are going to explain now, it assumes exactly that. It assumes that the movement is uniformly accelerated, and uses these formulas coming from a uniformly accelerated movement to compute the newer and newer values of the displacement all the time. Okay, so we have the new speed is going to be the old speed plus whatever the acceleration is times the time that has elapsed. I'm going to get some water. 1 second. Okay. In the same way, from high school physics, if you remember, we have that the displacement, or the position of a constantly accelerating particle, would be the, I'm forgetting the index here, but you understand. Would be the old position plus the speed times the time that has elapsed plus the acceleration times the times squared divided by 2, right? This is high school physics. And again, we see this formula reflected here. The new position will be the old position plus speed times time plus acceleration times squared divided by 2. They are the same formula. So we have assumed that the acceleration is constant to calculate the new speed, but the acceleration is an unknown, right? We don't know what the acceleration is, and this is another unknown. We don't know what the new speed is going to be, and here we have also the acceleration, which is an unknown, and we have a new position, which is unknown. The trick in the NUMERCS method is that these two values, the value assumed for the acceleration here and the value assumed for the acceleration here, mean they don't need to be the same, okay? Which from a physical perspective doesn't make any sense at all. Of course, the value of the acceleration used to calculate the new speed, which is this one, should be exactly the same that the value of the acceleration used to calculate the new displacement, which is this one, right? But for mathematical reasons that it's too complicated to go into, it is that you don't need to assume that they're the same. You can use different values there for these two different quantities, and this will result on a more accurate method. That was NUMERC's discovery, and that's why these kind of methods are called NUMERC's family of methods. Okay. All right, but how do we calculate this acceleration? Well, NUMERC uses this formula for the acceleration. Okay, which looks complicated, but it's really very simple. This is the acceleration at the previous time step. So the acceleration that we already know, that we have already calculated. And this is the acceleration at the new time step. So the acceleration that we're of the unknown point that we're trying to calculate. So what this entire equation here says is that the acceleration that we're going to use here to calculate the new displacement is going to be a mixture, a little bit of this plus a little bit of that, okay? And how do we mix them? How much we take of the first and how much we take of the second will be dictated by this parameter gamma, right? If we choose gamma to be 0.5, then of course the mixture is going to be 50-50. But we don't need to choose it to be 0.5. We can set it to other values, okay? And in the same way, when we have the formula for the displacement, we're going to use this expression got there to replace the acceleration here. Okay, let's see if I can manage to delete that red marking. Just as in the previous time, the acceleration that we're going to use here is going to be a little bit of the acceleration already known and a little bit of the acceleration that we're trying to calculate, the future acceleration that is unknown to us. In this previous example, how we mix those two, for this previous application, how we mix those two is controlled by the parameter gamma. In this other example, how much do we mix these two is controlled by this 2 times beta, right? If we choose to beta to be 0.5, then we have a 50-50 mixture, but we're not limited to that. All right, so we have now one equation number 1. We have another equation here, equation number 2. And these two equations we're going to carry to the next slide. All right. Here we have again, this is equation number, this is equation number 1. And here we have equation number 2. But we have 3 unknowns. We have the future speed that we want to calculate is an unknown. The future acceleration that we want to calculate is an unknown. And we also have the future displacement that we want to calculate. That is another unknown. So we need a third equation, and that third equation will be given by this, which is the equation of motion. Okay. Now we have 3 unknowns and 3 equations. As you can see, the equation of motion that we're satisfying, all the indices are I plus 1, I plus 1, I plus 1, I plus 1, and I plus 1. And it's this that makes this method implicit, okay? Implicit. We are satisfying the equation of motion not at the time step that we have already calculated, but at the time step that we are going to calculate. That is the difference between implicit and explicit methods. So now we have 3 equations, 3 unknowns, so we can, in principle, solve this. As in all previous cases, this assumes that we already know the properties of our structure. It assumes that we have chosen a delta t. Further, it assumes that we have chosen a gamma and the 2 beta factor. And it assumes that we know the loads for all times, okay? We need all these things in order to calculate this. I see a question, is it supposed to be ui plus 1, second row of equations? Do you mean in the previous slide or this slide? David, previous. Let's check. Here. Okay, never mind. Wait. And now, of course, the PowerPoint stopped working. Sorry, I'll have to fix it. Okay. All right, we were here. Okay. Someone asking why, if we can assume that if we go back to this slide, again, we're going to use the uniformly accelerated equation of motion to calculate a new speed and a new displacement. And here we have an expression for the acceleration. Do we have to assume that they're different? The answer is no. You can assume the same acceleration for both. But the, the point of Newmark's method is that you don't have to. That there are combinations, that there are ways of choosing A in the first equation and ways of choosing A in the second equation, which are not the same, but will lead to more accurate results. And exactly how, so in both cases, both here and here, A is a mixture of the previous known value and of the future value that we want to calculate, and how we mix those two is up to us. Of course, there are some good values of gamma and there are some bad values of gamma. You cannot choose whatever you want, but for some values of gamma and beta, the results will be extra accurate, which is the advantage with this method. I hope that answers that. And now we go to this. Just as in the previous time, we have some initial calculations on this half of the slide that we need to perform only once. We calculate an initial acceleration based on the equation of motion. And we calculate, again, these values k hat, a and b. They are not the same, of course, that we calculated for the previous method, because this is a completely different method. As you can see, all these values depend on what you chose for 2, beta, and gamma. They are all present here. And then we have the second half of the equation, which we need to loop, right? So for each time step that we want to calculate, we need to go through all these steps. And once we have calculated all of it, then we go back and proceed to calculate them again with our new values of the speed, the displacement, and the acceleration. And thus, every time we do a new calculation, we'll generate a new value for this. So as you can see, this method is slightly more complex than the previous one. It involves slightly more steps, and that is a characteristic of implicit methods that are normally a little bit more complicated, a little bit more time-consuming for the computer. And also in this method, we have to calculate the speed and the accelerations. In the previous method, the explicit method that we showed before, we could calculate it if we wanted it, but we didn't have to. But at least in this implementation of the method, we have to calculate them because they form part of our equations here. Okay, but just as in the previous method, we use the previous results that we have obtained again and again in order to generate new points, new data. Okay. As I have mentioned a million times now, so explicit method use the equation of motion at the time that we have already calculated and hope for the best. Implicit methods impose the condition that the equilibrium needs to be fulfilled wherever we land at the next time step. Okay? If we choose a delta t that is too large, both methods will lead to wrong solutions. Okay? The approximations that we make in the case of the central difference method, if you remember, is that the slope can be approximated by the one slope can be approximated by this other slope. So we have if we have a curve, the slope in this point can be approximated by the slope of these two other points. That was one approximation. And in the case of in the implicit method, numeric method, the assumption that we did is that the acceleration between 2 points is constant, right? Those assumptions are true if the delta t is very small, all right? And the larger it is, the farther from the true they are, and the more wrong that our results will be. Well, how wrong? Well, that depends. If you see in this line, if we have this is just a simplification, of course, but for delta t sufficiently small, the results were going to be accurate for both. If we have a delta t that is too large, at some point we're going to have inaccurate results. And if we choose a delta t which is larger than that, we're going to have results that are absurd. Okay. But this is only true of the explicit method. Okay. The explicit method, they can return absurd results. The implicit never does. Okay. And when I say absurd, I mean things that you're going to calculate the vibrations of your bridge, and it's going to tell you that the bridge is vibrating like 15 kilometers to the left and 15 kilometers to the right, which is obviously wrong. The implicit method is never going to do that. And I personally consider that to be a disadvantage, because with an implicit method, even if you use it wrong, your results are going to look good. If you use an explicit method and you use it wrong, it's going to be obvious that it's wrong. And that's good, that's helpful, because we can use that fact to correct our results, to choose a better delta t, all right? I'm going to now show an example. We have this structure, okay? The structure that has a mass, it has a stiffness, and it has dampening. All the values are given there in the table. So we can calculate its frequency of vibration, given that we know the mass and stiffness. We can calculate the value of the damping coefficient because we are giving the damping ratio. We have initial speeds and an initial displacement, 0, like it's normally the case. And, and we have a force, okay? In this case, I choose a sinusoidal force, but again, this method can be applied to any form of force, so it doesn't need to be limited to that. And here we have the results of our simulation done with the first method that we went through, the central difference method, which is an explicit method. And I have chosen to plot the result for 4 different delta t's, okay? We have a delta t of 0.1 here. And you can see that the result is very accurate. There are some differences between the actual result and the simulated result, but they are minor. And from an engineering perspective, they're not very important. I mean, if the bending moment is 1,000 kilonewton per meter or 1,001 kilonewton per meter, it doesn't really matter. Then we go the results at 0.2 with a delta t of 0.2. So this distance here has been chosen to be 0.2. And you can see that the results are much more inaccurate. They are not at all as close as they were in the previous, but it's still somewhat representative of the structure. And then we have the result for 0.3, and you can see that they're completely wrong. Like the green line doesn't follow the gray line at all. And finally, we have the results on 0.4. And here is what you can see, what I was talking about, that the results for a delta t that is sufficiently large, if we are using an explicit method, will be absurd. This curve is out of boundary. Of course, this continues up there and down here. So the vibrations in this case, or the method is telling me that the bridge is vibrating many, many hundreds of meters up and down, which is of course wrong. So again, with an explicit method, we can get accurate results, we can get inaccurate results, or we can get absurd results, depending on the delta t that we choose. And now here is the results from NUMERX. Again, we have the accurate solution with delta t of 0.1. We have a slightly more inaccurate solution with a delta t of 0.2. We have 0.3, which is more accurate than in the previous method with a 0.3, but and then we have the 0.4, which is completely wrong. Again, in the previous example, this plot was completely ridiculous, and it was very easy to see that it was wrong. In this example, it's harder to see. Of course, when you're calculating a structure, you don't have the gray line. You don't have the result. You don't know how it's supposed to look like. So it would be very hard to just look at this line and just discover that it's wrong. So that is one disadvantage, really, of the implicit method, that you can get the wrong result and not notice it. But this is calculated for a given value of beta and gamma, right? And as I told you, these two, the beta and gamma, we can play with them a little bit. If I choose some different value for them, as in this picture, again, this is Newmark's method, which is implicit, but now I'm using a slightly different beta. Gamma is still the same. And you can see that the results get more accurate. The results are fairly accurate for 0.1, 0.2, 0.3. They're still kind of okay for 0.4. Probably not close enough, but it is a better choice of beta and gamma for this particular problem. Okay. Let's. It's now 11, so let's do I'll pause the recording and we'll do a 15-minute pause. All right. So let's continue with our lecture. We were comparing the accuracy of different of the two different methods that we talked about. We had first this slide showing how it worked for the explicit method that we went through, central difference method. And we could see that we could obtain accurate results, as in this picture here, or inaccurate here, and completely absurd results, as in here. And in my opinion, that is a good thing, because it allowed us to notice when our results are wrong. And then we have the Newmark's methods, which give more accurate results and never get absurd results for whatever delta t we choose. And I showed you how we can pick different values of these parameters beta and gamma that we need to choose for our Newmark's method. But one thing that I didn't mention is that in practice, when we are talking about single degree of freedom system, when we're talking about a single degree of freedom system, the delta t that we choose doesn't really matter, because the calculation, I mean, it does matter in a mathematical sense, but it does not matter in a practical sense, because the calculations are so fast in any computer that it will take milliseconds to do no matter what you choose. If you were to do it by hand, then you should be more careful, because choosing a larger delta t will save you a lot of time. But in a computer, it doesn't make any sense. And for that, I wanted to show you this slide, in which I have plotted the exact value of the displacement and the displacement using the central difference method and the Newmark's method. And you can only see one curve because they are all on top of each other. They are practically exactly what the theoretical result is. And they are, and I choose a delta t of 1 over 10,000 of a second. And it took the computer this much time to calculate. So of course, it doesn't make any sense to choose a larger delta t for this case, for the case of a single degree of freedom, because the calculations are very, very fast. As you can see, there are, I don't know if you can see it in your screen, but at least in my screen, I see a little difference here in that area. But otherwise, it's almost exactly the same. Okay. But of course, when we are dealing with structures, we are almost never dealing with a single degree of freedom system. Okay. We have multiple degree of freedoms. And that changes everything a little bit. When we have multiple degree of freedom, then we have to maybe start thinking more about the delta t. And that is for a reason. If we go back to this slide, for a single degree of freedom, we have a value for the displacement, right? And we have a value for the stiffness, and for the mass, and for the damping. And these are all numbers, so we can operate them how it's described in this slide. But if we have a multiple degree of freedom system, then let's say we have a structure with 100 degree of freedom, which is very little actually. In practice, when we do a finite element model of a structure, we're going to probably have thousands of degree of freedom. But let's say that we have 100 degree of freedom, then our displacement will be a vector, which is 100 long, okay? And our stiffness will be a matrix, a stiffness matrix, which is 100 times 100. And the same is true for the mass and the stiffness, okay? And as we can see here, so this value here, it's also going to be a matrix, because it's the result of one matrix, this one, M is a matrix, so this expression is a matrix. And this one, C is a matrix, so the sum of two matrices is going to be another matrix. And here we are dividing by K hat. And of course, in order to divide for a matrix, you need to invert it, right? So this value here is 100 times 100. And every time you inverting a matrix is very, very, it's a very computer intensive process. So for every time step that you choose, you would have to theoretically invert this new matrix every time. And that takes a lot of time. So calculating a system of 100 by 100, then one need to choose the delta t with more care. For the exercise, you're gonna, some of the exercises, you're gonna have to model a bridge, which will result in something like 30 or so degrees of freedom. So for those quantities, it's not a problem. But it's something that needs some thought if you're either working by hand or if you're working in a system that has a very large number of degrees of freedom. All right. So the practical besides the practical way of programming it, that you can see in this slide and in the previous slide, I think this is also an important slide, okay, that you need to understand. You need to understand the difference between implicit and explicit, and you need to understand when your method will give an accurate answer compared to an inaccurate answer. So this is like theoretical knowledge that is important to have, and that would normally come in the exam also. This, of course, you're not going to be asked to program anything in the exam, but you will in the exercise. So this is also things that it's good to have an understanding of. This took a little bit longer than I thought. So I'm not going to have time to go through Duhamel's integral, which was the last point. But it's yeah, it's a mathematical way of calculating the same thing, but it doesn't have a practical application, because normally when we compute the response of a structure, it is almost always with a time stepping method. So I'm gonna skip over this last part and open for questions in the chat. Hopefully with, yeah, if you have any questions, just put them in the chat. I'll try to go through as many as I can, but I'll give you a few minutes. There are, it will depend on, so the question is, are there criteria to select the values of gamma and beta? And the answer is yes, but they are, it's a little bit complicated. It depends a lot on the kind of problem that you're solving, okay? For this course, we're going to use two values, two specific values of gamma and beta. One is choosing gamma to be half and beta to be 1/4. Why? Because that results, if we go back to this equation here, if I choose gamma to be half, then that results in the assumed acceleration A to be the average acceleration, whatever the average between the previous point that I've calculated and the new point that I want to calculate. I assume the acceleration in between to be the average. And I'm assuming the same for this value of the acceleration and for this value of the acceleration, which is the most intuitive answer, right? It's the one that you would probably, if you have to guess, you would guess that. The other value that we're going to use is 1/6. Also, gamma is still 1/2. It's always 1/2, but beta is 1/6. 1/6 is good because it results in a linear, in an assumption that the acceleration is linear. So if I have my axis here, and I have my curve that represents the accelerations with time, and I have calculated a point in time, and I want to calculate the next point in time. If I choose a beta equals to 1/6, 1 divided by 6, then that simulates, or it's the same as assuming that the acceleration varies linearly along. It's hard to see. Let me choose another color. Maybe very light. It's the same as assuming that the acceleration varies linearly here. Okay. For other types of problems, you would need to have a look at the eigenfrequencies of the problem and stuff like that. But these two values are normally very common and kind of, at least in an intuitive sense, makes sense. So that is the two values that we're going to use, and those are the two values that you see being used here. So this is what is called the this. These values result in the average acceleration and these values result in the linear acceleration assumptions. More questions? Sure. I'm assuming it's this one, I mean. You're gonna get the PowerPoint eventually also. I'm surprised that it's not, because it's the same PowerPoint every year, so it should already be in the system. No, it will not be me at the exercise. It will be someone else. All right. There doesn't seem to be any more questions. I'll stop the recording, and I have one more lecture, but that's a bit ahead. I'll give also the lectures about earthquake and how we simulate earthquakes. But yeah, that is all for today. So thank you for attending, and I'll upload this video to Canvas so you can all have it. So bye for now.